Okay, hi, Assalamualaikum everyone. So today we are from group 4. We would like to present about metallocarbораnes. And my name is Maisara binti Asmaon, and my group members are Nur Aiza binti Badru Hisham, Nurul Afa Fatima binti Nazmi, Nurul Atika Izati, and also Darchayani. So here is our outline. We have introduction, synthetic roots, structure and names, bonding, and also reactivity. So let's start this. This is the introductions of the metallocarborane. The definitions is a carborane, which is a compound of carbon, boron, and hydrogen, which is containing one or more metal ions such as nickel, ferrum, and also cobalt. Usually, F and D block metals form together with carboranes, and typically we can see the metallocarborane is a sandwich of two carboranes with a metal ion in the center. And we can also say that the metallocarborane will known with the 13 to 15 vertices, but usually we can see the 14 vertices metallocarborane. So, metallocarbораnes becoming subject of chemical community for their unique combinations of features and properties, such as the first one is the rigidity of the cages, the second one is the relative rotary motions, the third one is hydrophobicity, and the fourth one is the chemical and thermal stability. Here we can see the delocalized charges and also the electron transfer. Okay. So let's proceed with the synthetic roots of metallocarborane with my friend's presentation. Thank you.
My name is Atika. Now I would like to proceed on the synthesis routes of metallocarborane. The six listed here are the example of main routes of metallocarborane. Firstly, it is the coordination using nidocarborane ions as ligands. Second is the polyhedral expansion reaction. Thirdly is the polyhedral contraction reaction. Fourth is the polyhedral subrogation. Fifth is the thermal metal transfer reaction. And lastly, it is the direct oxidative insertion of a metal center. So, for the coordination using nidocarborane ions as ligands, the reaction of C2B9H11 with FeCl2 in the presence of tetrahydrofluorine with exclusion of air and moisture will give us the dimagnetic base sandwich type complex of Fe2+. When this reaction is reversibly oxidized, it will give us the corresponding of the Fe2 plus complex. When this reaction is carried out in the presence of NaC5H5, it will give us the purple mixed sandwich complex. So this reaction is general and have been applied to many transition metals as well as lanthanide and actinides. Next, we proceed to the polyhedral expansion reaction. This reaction involves two electron reduction of a chlorocarborane with a strong reducing agent. This reaction is quite general for chlorocarborane, which involves the reductive opening of a N-vertex chlorocluster followed by metal insertion. Lastly, we proceed to the polyhedral contraction. This reaction involves the removal of one BH group from a chlorometallocarbonate by nucleophilic base degradation and followed by the oxidative closure of resulting nidometallocarbonate complex. This reaction is however not preferred to prepare because metallocarbonate will degrade completely under these conditions. So that's all from me.
Hi, so now I will present to you about the structure and names of metallocarboranes. So first, metallocarboranes can be considered as either molecules in which a metal replaces one of the boron verticals or as a metal with a carborane ligand bound to it. Second, one of the example of a metallocarbonane is the icosahedral metallocarboranes. It is generally made by decapitation of chloro-C2B10H12 to give a nidodianion. For example, so the example of nidodianion is 79-nido-C2B10H12 2-, followed by metal metallation with an appropriate metal fragment. So next is the example of chlorso C2B10H12. So here you can see three structures, which is the orthocarborane, metacarborane, and also paracarborane. So the position of the carbon which differentiate these three structures. So next, this is the example of structure of metallocarborane. So here is the structure of iron cyclopentadienyl carborane. So here the black one shows the CH bonds, and the white molecule shows the BH bonds, and this is the cyclopentadienyl, and this is the iron. The other example of metallocarborane is this one. So first, this structure we react with zinc Me2. So we get the structure of metallocarborane, which contains Zn. It is highly planar. Zn2b2 dimer-like structure, and also weak zinc-zinc bond. So that's all from me. Thank you.
My name is Nur Aiza binti Baru Hisham and my metric number is 192645. So I will proceed about the bonding in metallocarborane. So typical metallocarborane is a sandwich complex in which a metal center ion, commonly cobalt or ferrum, is theta 5 coordinated by two dicarbonate anions. This is the example of the structure of the metallocarboranes. The black one is the carbon, while the white one is the borane. And this is the metal between the two sandwich complex. So from this structure, we can see that the metal is linked to the cage. This is the cage via boron, metal, boron, bond. Boron, metal, boron, bond. Another bond that occurs in this structure is boron and hydrogen, because we have 11 hydrogen in each case. So boron with hydrogen, carbon with hydrogen, boron with boron, boron with boron, and boron and boron, like this one, the three boron that connect to each other, and boron carbon. So we can replace the cobalt with another metal, but by replace with this, we can change the charge and redox properties. The metallocarbon forms strong bond with transition metal. Metallocarbon tend to stabilize lower oxidation state of transition state of element of these elements. So this is another example of metallocarborane. This is iron. As you can see here, we can see the metal with boron bond, metal with boron, and metal with carbon, and carbon with hydrogen. The hydrogen is here, somewhere here, and boron with hydrogen, boron with boron, and boron with carbon. So bond of metallocarborane versus metallocenes. What is metallocene? Metallocene is a compound consisting of two cyclopentadienyl anion. This is an example of structure of metallocenes. The anion work much more efficient in anion A compared to anion B. Anion A is a metallocarborane while anion B is metallocenes. Thus, when anion A work much more efficient than anion B, it shows that metallocarborane is much more stronger than metallocenes, lead to more stable structure of metallocarborane compared to metallocenes. So that's all from me. Thank you.
Presentation Aiza.
Hi, my name is Darshini Kasinathan and my metric number is 194330. I will proceed the presentation with the reactivity of the metallocarborane. Due to the Vicker's reducing power of 12 vertex carborane, it leads to the synthesis of supercarborane. Supercarborane is also a metallocarborane but with more than 12 vertices. Examples are 13 and 14 vertex metallocarboranes. So let's take a look at the reactivity of the 13 vertex chlorocarboranes. They can be reduced to the corresponding nidocarborane dianions by excess group 1 metals, where in this case the group 1 metal can be sodium, potassium, lithium, and etc. Group 1 metals are very useful syntones for the synthesis of metallocarboranes of P, D, and F block elements. So synthone is actually a constituent part of a molecule to be synthesized. They can be reduced by alkali earth metals like calcium, magnesium, and etc. Exhibits nucleophile dependent reactivity because the 13 vertex chlorocarborane have different reactivity patterns which are dependent on the nature of the nucleophile itself. Stronger electron withdrawing units than the 12 vertex one because 12 vertex chlorocarborane cannot be deprotonated by the strong base. However, for the 13 vertex, since it's a stronger electron withdrawing group, it can exhibit a fast and reversible deprotonation, but slow nucleophilic addition. Moving on to the next slide, which is about the reactivity of the 14 vertex chlorocarborane, it is less reactive compared to the 13 vertex one, easily reduced by group 1 metals. Reducing power of the carbon atom adjacent nidocarborane dianions, which are synthesized from the chlorocarboranes, increases as the cluster size gets bigger, which means that the reducing power of the nidocarborane dianions increases from 12 vertex to 13 vertex and to 14 vertex. So from here we know that the 14 vertex nidocarborane has the highest reducing power. However, 11 vertex nidocarborane is redox inactive. So these are the structures of the 13 and the 14 vertex chloroclusters. These are the references. That's all from us. Thank you and have a nice day.